All right, so really today is kind of the qualitative look at solid state. So yesterday we focused a lot more on the kinds of quantitative calculations. We looked at how do we view a unit cell, how do we determine how many atoms are in a unit cell, all of that kind of stuff. And so for today, we're going to look more at the qualitative side of things. And this is what we will ultimately wrap up this chapter with. And this is also the last series of concepts that we will be bringing up in this course. So we're going to start with a concept known as band theory. Now, band theory comes as an open derivative of something else called molecular orbital theory. Now, molecular orbital theory is a more correct way of describing how atoms change themselves to form molecules. So back in General Chemistry 1, Chem 105, we talked about the idea of hybridization. We talked about the formation of these hybrid orbitals, and the hybrid orbitals give us these shapes, which give us these bond angles and predict all of this stuff. And from a modeling standpoint of determining the bond angles, hybridization does a really good job of explaining that. What hybridization does a poor job of is actually talking about the mechanics of how to get there. We oversimplify incredibly when we talk about hybridization. You know, we're not taking these atomic orbitals and putting them into a blender and out come these perfectly shaped, perfectly oriented hybrid orbitals. What happens more at the molecular level is we get this formation of these molecular orbitals. And these molecular orbitals have a couple of things that are associated with them that are kind of interesting. And we'll get into more of the details. If you take organic chemistry, we'll talk a lot more about these orbitals and how they relate to bond order and how they relate to a whole bunch of other things. But what we really need to understand here is that when we have electrons in these orbitals, basically we can think about, let's take a look at sodium here. Sodium's electron configuration is neon 3s1 and then 3p0. If I put two sodiums together and they make a metallic bond, well, now I have 2s orbitals and 6p orbitals. And what we start to see is that they will start to split into two different camps. One camp is lower in energy and conducive to bonding. We call those bonding orbitals. And another camp is higher in energy and less conducive to bonding. We call those anti-bonding orbitals. And so you can start to see the split between the bonding down here and the anti-bonding up here, not only in the S subshell, but also here in that P subshell. And the more that we add, the more of these orbitals we're going to create, and they're going to end up creating for us a band of filled orbitals. That's down here depicted by this purple, and partially filled orbitals that's depicted here by pink. And there will also be a band of completely empty molecular orbitals that are shown here in gray. Now, in metals, what happens is that these bands, this valence band, the band that has electrons in it, overlaps in size with the empty band, the conduction band. And so because of that overlap exists, the electrons are able to freely move from any of those molecular orbitals to any of the other ones if they are provided enough energy. And that's what gives metallic substances their conductivity. They have this free movement of electrons because they have this completely continuous band of orbitals for those electrons to move through. So we can kind of simplify the whole thing here. And instead of looking at it as kind of this three-tiered system here, where we've got filled, partially filled, and unfilled, we can kind of break it down into there are filled orbitals and unfilled orbitals. And we call that group of unfilled orbitals the conduction band. So we've got the valence band that has all the electrons in it, and we've got the conduction band that doesn't. And if those two bands are continuous, if they run into each other, if there is overlap between them, then we will see conductivity, at least in terms of electricity. That is what sets apart a conductor from a non-conductor, is this overlap of those valence and conduction bands. Now the question becomes, what if we don't have that continuous band? What if the conduction band and the valence band don't overlap with each other? What if there is a gap between them? Well, if there is a gap between them, we call that a band gap. The band gap is a specific amount of energy that exists between that group of orbitals with electrons in it and that group of orbitals that is empty. The larger the band gap is, the more unlikely it is that a substance is going to conduct electricity. So if you look at good insulators, insulating materials have large band gaps because the band gap is just too great for those electrons to jump across. But for substances that have a relatively small gap, what we can do is we can create something called a semiconductor. A semiconductor takes advantage of the fact that there is a relatively small band gap for a given substance, and it basically introduces another substance into the matrix that is going to help that substance cheat its band gap a little bit. And there are two different ways that we can cheat the band gap. We can do what's called an N-type semiconductor. In an N-type semiconductor, we're going to introduce an atom that has slightly more electrons in it. And so what it's going to do is it's going to raise that valence gap or raise that valence band and minimize the gap by erasing that band. There's also a p-type semiconductor. A p-type semiconductor kind of does the opposite thing. We introduce an electron poor substance, and what happens is that electron poor substance has a lower conduction band, and so it's easier for the electrons to jump across as a result. So what does that look like in terms of, pictorially? How do we get to that spot? Well, it looks kind of like this. Here is silicon. Silicon on its own does not conduct electricity very well. Doesn't really conduct it at all under most circumstances. And the reason why is it's got a decent sized band gap here. But silicon can be doped. That is, we can add to its conductivity by adding stuff to it that is going to change that band gap. And so with an N-type semiconductor, we can introduce phosphorus. Notice that phosphorus and silicon are both on the same energy level. They're both in that third row. Phosphorus has one extra electron. What does that extra electron do? Well, it raises the valence bond. It raises that valence band, and now instead of that gap being the super gigantic EG gap that we saw, now the gap is just this right here. Not complete overlap. We're still not going to get full conduction in terms of what we would expect out of a metal in this semiconductor, but it's a heck of a lot closer. Close enough, in fact, that this particular type of semiconductor conducts electricity okay. Yes, there's a little bit of resistance, but certainly not nearly as much as there would have been with the pure silicon. Now, what does a p-type semiconductor do? Well, now we're going the opposite direction. Instead of having something that has more electrons in it, we're going to add something that has fewer electrons in it. What do those fewer electrons do? Well, they move the conduction band downward. I don't have a gray color on this, so we're just going to have to make do with the blue here. But they're going to lower this conduction band down. So that all that the electrons have to overcome now is that little gap right there. Again, not perfect, but a heck of a lot better than it was. And that's kind of the important thing to know with semiconductors, is that it's going to get us a lot closer to where we're supposed to be. It's not going to give us perfect conductance. It's not going to give us complete overlap most of the time, but it is going to make things a lot better, a lot easier from an energetic standpoint. Now, how do you keep them straight? Not a really good explanation for either of them. But we do need to understand the N type is going to have an extra electron. The P type has more holes, so it's going to have fewer electrons. That's what we're going to do. So as far as what you might see, the homework assignment tonight focuses on semiconductors, focuses mostly on kind of doing the difference between P-type and N-type, recognizing conduction bands and so on. So you'll see that there. As far as the quiz is concerned, tomorrow, you're going to have one question on there about semiconductors, and it's going to be on the construction side. I have this element, and I want to make a P-type semiconductor. What do I need to add to it? And the answer to that question is you look at the periodic table, and it's one of the next door neighbors. So if you are looking at a P-type, you go one spot to the left because you need one fewer electron. If you are looking for an N-type, you go one spot to the right because you need the extra electron. But there's only one correct answer for that kind of question. Because you can't jump energy levels, you can't have too many in there. You don't want the conduction bands to get thrown off too much. All right, the rest of this chapter is going to focus mostly on just the presentation of a variety of different ionic solids, a variety of different solid materials, and how they're constructed, and how we can use kind of the concepts of unit cells that we saw yesterday to investigate their structures a little bit more fully. So for example, we're going to talk about ionic solids. Now, ionic solids are going to resemble in a lot of ways the unit cells that we discussed yesterday. The difference between the ones that we saw yesterday and ionic solids is the fact that we're going to have different interactions because we're not talking about all the same atom. So usually what we will see is that the anion, because it is larger most of the time, that is going to be the thing that kind of makes the structure of the unit cell. So we will often see that for ionic solids that make cubic unit cells, it will be the anion that is on the corners of that cubic unit cell. Now, the anion might make a body-centered or a face-centered design as well, but generally we're going to see simple cubic a lot from that standpoint, with the cations kind of filling in whatever holes that they can fit into. So when we talk about coordination number for ionic compounds, what we have to talk about instead of how many things does it touch is what is the relationship between the cations and the anions? How many cations are there? How many anions does a given cation touch inside of the structure? Like we saw with our unit cells yesterday, coordination number has a lot to do with stability. Yesterday we talked about it more from a packing efficiency standpoint. Today we're talking about it more from a stability standpoint. The more interactions we get, the more ionic intermolecular forces that are being generated, the more stable the structure will end up being. but the value of that coordination number does depend upon size. We know that the anions are larger. Like I said, they're gonna generally form the cubic structure of our cell. The cations are gonna kind of fit in between wherever they can go. Closer they are to each other in size, the higher the coordination number is going to be, because they're going to make more interactions as a result. So we take a look at this first example here, cesium chloride. Now, cesium chloride kind of resembles a body-centered unit cell. The only thing that is different is that we've got two different substances there. We've got the simple cubic being represented with those chloride ions, and we've got the cesium ion in the middle of that cube. And so if we follow our general rules for atoms per unit cell, what we end up getting is that since each one of these is on a corner, they are each worth 1/8 of an atom. And since the cesium is inside the interior, it's worth 1 atom, which gives us our chemical formula, cesium chloride, CsCl, 1:1. Now, the coordination number here is 8, because you can see that this cesium being in the middle of this body is going to be touching 8 chloride ions at the same time. We know from yesterday that this interior hole here is called a cubic hole because it is inside the cube. And so this is giving us something very similar to, again, body-centered is kind of the closest analog that we have. The only difference is that we've got a cation in the body and anions making up the cube. They are different substances. For rock salt, so sodium chloride, our coordination number here is 6. So it is not nearly as stable as the cesium chloride is, even though it is smaller. But because it is smaller, notice that what we can get out of this cubic arrangement. The chlorides are actually arranged in a face-centered cubic orientation. So if I look at the unit cell, remember, face-centered cubic is 4 atoms per unit cell. So I've got 4 chloride ions in here. And each one of those sodium ions, the ones that are depicted there in purple, those are fitting in octahedral holes. Octahedral holes because you can see each one of these sodiums is touching 6 chlorides. So if I look at this one in the middle, I see 1, 2, 3, 4, 5, 6. 6 chlorides that each one of those sodiums are touching. And so that's where this octahedral hole idea comes from. Remember back to your molecular shapes. That molecular shape that had the 6 things coming off of it was octahedral. And here we see it in this ionic crystal now with the sodiums. So if you do the counting there, what you'll see is that you've got the 1 sodium here in the body plus a whole bunch of these here on the edges. And remember that edge ions are 1/4 atom per cell. So I've got 4 edges here, 4 edges there, 4 edges there. So 1 plus 12 edges times 1/4 each. My unit cell has 4 sodium ions, 4 chloride ions. And so if I break that down into the simplest form, this is where we get the formula. Sodium chloride is NaCl. Now, one of the reasons why we can get this particular structure for the sodium chloride and we couldn't get it for the cesium chloride is obviously the size. The chloride ions at 181 picometers and the sodium ions at 97 picometers are a good bit smaller than the 167 picometers for the cesium. That doubling in the size of cesium almost makes it very difficult. It can't fit into those octahedral holes. The only holes that it can fit into are the cubic holes, which is why it forms this body-centered kind of orientation. So size really does matter in this kind of way. And so what we'll get out of this is, even though we are not getting as high of a coordination number, we are getting a good bit more closeness because of the size thing. And we're getting a more compact structure as well. So we should expect that the density here is going to be comparable, if not better, for the sodium chloride, just because of the size thing, because they're going to be able to have a greater packing efficiency. The only thing that would keep it from truly being greater is because cesium is a good bit heavier than the sodium is, by a factor of nearly 5. Zinc blend. Zinc blend is an interesting structure. Here we have a coordination number of 4. If you look at the sulfides, so the sulfides are these gold colored atoms here. You can see that they are arranged in a face-centered cubic arrangement as well. And so for the sulfur as a face-centered cubic, we would see 4 sulfide ions in the structure. Now the zinc, because the zinc is at 74 picometers, isn't terribly large. In fact, we look at it compared to the sodium. It is smaller than the sodium. But because of the sizes of those sulfides, we're going to see that the octahedral holes are not nearly as available because of that size. So what we're really looking at here is they're going to occupy the tetrahedral holes. So in those tetrahedral holes, you'll see that this zinc is attached to 1, 2, 3, 4 sulfurs. Now, those tetrahedral holes are all inside the interior body of the unit cell. So we can see that there are 4 zinc ions inside that body of the unit cell, which match the 4 making up the actual construction of the cell. So a 4-to-4 ratio, same as a 1-to-1 ratio. Zinc blend would be ZnS, which is exactly what we would expect it based off of its charge. Fluorite. Fluorite is calcium fluoride. Now, fluorite's an interesting setup. We actually see kind of the reverse here, where we are seeing, instead of the anion making up the structure, it is the smaller cation that is making up the structure instead. So what happens is we've got the calcium ions in a face-centered arrangement. So that will give us 4 calcium ions as a result. Each of the fluoride ions is going to fit into one of those tetrahedral holes. So you can see each one of those fluorides is touching 1, 2, 3, 4 calciums. Now, inside of a face-centered unit cell structure, there are 8 octahedral holes, or excuse me, there are 8 tetrahedral holes inside of that structure. Now, in the zinc blend, because of the size, we only saw half of them get occupied. In fluorite, because the fluoride ion is on the smaller side, and the way that the arrangement is here with the calciums, we're going to see that the fluoride is able to fit into each and every one of those tetrahedral holes. And so we'll end up with 8 fluorides in total, because again, each one of those tetrahedral holes is on the interior of the cell. And so with 4 calciums and 8 fluorides, this is where we get calcium fluoride, CaF2. And so this particular structure is very common when we have a 1-to-2 ratio for the cation to anion. So this would be other ion compounds of similar type, magnesium iodide, or sodium, beryllium fluoride, or calcium chloride, or any of those. We'll tend to see this structure for that. Now, if it's reversed, if it's like sodium sulfide, where it's a 2-to-1 ratio cation to anion, what we'll see is something called the anti-fluorite structure, which will look exactly the same, but the cations and anions will switch positions. So you'll have a structure more like what we're seeing, or what we've been used to. Anions make up the face-centered unit cell. Cations fit into those tetrahedral holes. All right, so let's switch off from looking at these substances, these ionic compounds, and let's look more at some other kinds of compounds. So let's look at molecular compounds now, more in particular. And what this comes to is a concept of allotropes. Allotropes are molecular compounds that have different molecular structures for the same kind of given element. So the most common form that we know of is diamond. Diamond is a common allotrope of carbon. In diamond, what we have is something called a network covalent solid. And network covalent solids are really common for some of those solid materials that are non-metallic. Basically, what we have there is, instead of thinking of these substances as individual atoms that are packed together kind of like a metal, we need to think of them more like covalent compounds. And so what we look at in diamond is we see this repeating pattern inside of the diamond of each carbon atom being bonded to 4 other carbon atoms. And since we have that, what we have in diamond is a large series of tetrahedral carbons all bonded together. And the net result of it is rigidity, because you've got all of these carbons basically forming this net, and non-conductivity. But there are other allotropes of carbon as well. We're familiar with graphite. Graphite is the thing that is what makes up pencil lead. In graphite, it's still a network of carbons, but instead of this tetrahedral configuration, what we see is that each carbon is bonded to 3 other carbons, and we make these series of sheets of all of these different planar rings. And those planar rings are loosely attached to each other, loosely associated with each other, to the point where, they're held together by London dispersion forces. What that does is it gives graphite its kind of slippery feel, because those graphite planes can just slide over each other. And so in sliding over each other, that's why graphite is able to be used as a pencil. You're basically just smearing it onto your paper because it's relatively soft as a solid. And it's also why graphite can be used as a lubricating item as well. You build up a layer of graphite there, it gets slippery. Why is it slippery? Well, it's slippery because those layers of rings are just sliding over each other. And so long as you keep it there, they will continue to slide. We also see that there is some conductivity inside of the graphite molecules as well. Now, closely related to that is something called graphene. Graphene is a single layer of graphite. So if we take that ring structure and remove all of the other rings and just focus on a single layer, that is what graphene is. And to the note, it is among the thinnest yet strongest materials available. Now, in addition to those, we also know about fullerenes. Fullerenes, named after Buckminster Fuller. I'm not making that up. What we have there is another network covalent substance, but instead of this series of tetrahedrals or this thin series of sheets, basically what you have is a soccer ball configuration where each one of those is bonded to 3 other carbons. And what they do is they form these rings that, instead of being planar, they basically scoop up around each other and form these spheres. And again, it is a soccer ball configuration. You can see that basically we have around every single 5-membered ring, there are clusters of 6-membered rings going all the way around. Very similar to what you would see on a soccer ball. The black patches on a traditional soccer ball are hexagons, or excuse me, pentagons, and the white patches are hexagons. And it's kind of the same pattern. Now, Fullerenes are relatively new in their discovery. And by relatively new, I mean 40 years, which is very quick in scientific time. And we know that they are present in soot. They also have a number of different cool applications, most notably nanotechnology. Nanotechnology is largely based upon this idea of these fullerenes that are being used and kind of synthesized into tube-like structures or into other kinds of structural materials. And there have been a lot of strides made in nanotechnology, especially in the last 20 years or so. One of the things that they do have going for them, because they are kind of graphite derivatives, we do see some conductivity behavior. They act more in the semiconductor kind of range. Their durability is what is most notable. They have a good amount of tensile strength, which does put them into an elite class of materials chemistry. Now, phosphorus also has a number of different allotropes associated with them as well. Maybe not as exciting or cool as all the different forms of carbon, but there are a number of them that do work and do have some interesting kinds of concepts with them. And so with phosphorus, we can see in white phosphorus, we have kind of this four-membered cage molecule, P4, where you can see each one of those phosphorus atoms is attached to the three others. They make these P4 molecules that are sp3 hybridized and form these weird little tetrahedral cages almost. The form of phosphorus we're most familiar with is the red phosphorus. Red phosphorus is the white phosphorus form, but we have connected those little cages to each other in kind of like a polymer strand kind of fashion. And that strand is reactive and flammable, but not nearly to the same degree as the white phosphorus is. White phosphorus is pyrophoric. It will react readily with air and burn quite violently when it does so. Red phosphorus will burn. It's in match heads. It's in a couple of other things like railroad flares and blasting caps and some other things like that. But not to nearly the same degree in terms of the intensity of the reaction. Black phosphorus, on the other hand, we can see we've got a much more stable ring structure here. And this one is not nearly as reactive as the others. Silicates. Silicates are ionic compounds. Well, excuse me, not ionic, molecular compounds of silicon and oxygen. These kinds of compounds make up the majority of the stuff in the Earth's crust. This is what we find in sand, which we certainly know a lot about around here. Dig into the soil, you're going to find good, healthy spoonfuls of it. But what you can see in the silicates here is that they are network covalent substances. So they just look like this large network of all this stuff bonded together. But they do fall into kind of like a unit cell structure, where you can see that there is one silicon and 4 oxygens present. That unit cell structure is kind of the same. Now, that's not to say that that is the actual formula of the silicates, because what we have to understand is that each one of these oxygens is bonded to 2 silicons. So it's not SiO4. Those 4 oxygens are shared. So it's really only 2 oxygens per silicon. It's SiO2. SiO2, we know that, silicon dioxide, from a mineral standpoint, we call it quartz. So the silicate structure here, this network of covalent compounds gives us the mineral quartz, which we know does a lot of different things, from building materials to the precursors for making glasses. There are lots of applications to quartz, and it happens to be really, really common in the ground. So from silica, we can get some polymorphs. Polymorphs are just different crystalline structures of the same molecule. So one of the polymorphs of silica is SiO2. This is the kind of crystalline form of quartz. And we can see in this crystalline form here, we get this very ordered arrangement. And that very ordered arrangement gives us optical clarity, which is why quartz has that see-through appearance, very much in the same way that diamond has that see-through appearance because of the way that it's structured, and the rigidity of that structure and the way that light is able to pass through it. We get into other polymorphs of silica, and we can see that if we change that structure, we go from this ordered state to this more disordered state. That optical clarity disappears. It's the same substance, at least compositionally, but structurally there are differences between the two. And that's what's showing itself here through these different pictures of these rocks. There are also ionic versions of these silicates where we can get the silica to take on electrons and bond, in the case here with aluminum. In the case down here, just creating a silica matrix. And folks, that's it. That's all she wrote for solid state. So if you read in chapter 18 in your book, there's a lot more in there. Like I said, we're kind of taking a bird's eye view of solid state, primarily because this isn't a course that is designed specifically for chemistry majors. If it were, we would talk a lot more about solid state kinds of things because there would be broader applications down the road for those students. But since we're talking more generically here, again, thinking about what is it that we're going to see on that quiz tomorrow? What is it that we're going to see kind of moving forward? Unit cell calculations, being able to look at a structure like look at a structure like this and derive its chemical formula by looking at, okay, that's face-centered cubic, so there are 4 atoms in it. Oh, those are edge atoms, they're a quarter each. Those are face-centered, they're a half each. There's a body center, that one's 1 each. Being able to just look at it that way and say, okay, I've got a structure, I know that this is that, and the green balls are this atom and the blue balls are a different one. What is the formula? being able to do the calculations that we did yesterday, edge length to radius, radius to edge length, density being tossed in there in the middle somewhere, and being able to identify semiconductors, p-type, n-type, and just kind of know a little bit of something about them. That's what you need to focus on for tomorrow. Everything else in that chapter is kind of good information to have, but it's not going to be the thing that ultimately fixes us in one way or the other for the final exam. So that being said, we will end here.